You likely used Apache Arrow today, but you almost certainly didn't know it because nobody installs it on purpose. It arrives inside DuckDB, Polar, Spark, Pandas 2.0, BigQuery's Python client, and most of the other tools that are sitting in your requirements file. And it's totally fine until the day you're looking at two pipelines that do the same job, and one hands data between tools instantly while the other takes 4 minutes. Then it stops being trivia and starts being something you might want to learn. So that's what I'm going to talk about today, right? And let me just kind of show you the problem I'm talking about before I define anything. Let's say you've got a Spark data frame with 10 million rows, and you want it in Python as a pandas data frame. So you want it because you want to do something that Spark is bad at. So you call two pandas. With arrow off, that's 4 seconds, right? But with arrow on, the same data, the same machine, the same cluster, it can be under a few milliseconds. And nothing's going to happen in nothing's going to change except one line of config, right? And so what's happening there is Spark is holding that data in the JVM in the slow version in its own memory layout, and Python has no idea what a JVM object looks like. So Spark walks every row, it converts everyone to a serialized byte stream, it ships it over a socket to the Python process, and then Python walks the whole thing again to rebuild it as Python and NumPy objects. So 10 million rows in and 10 million rows out, and that's the serialization tax. You have two full passes over your data that produce nothing, where you didn't filter or aggregate or compute anything, you just burned CPU memory translating the same numbers from kind of one dialect to the other, and it's just still the same numbers. And for most of the last 15 years, that was just kind of the cost of doing business because almost every tool had its own end memory layout, right? Pandas used NumPy arrays with a Python object escape hash for strings. R had vectors, Spark had JVM objects, and then it's got Tungsten's binary format. Postgres had rows, and all of those are reasonable decisions in isolation, but when you put 10 of them in a pipeline, you've got a translation layer at every boundary. And 10 tools means like 100 different possible converters, and someone then has to write and maintain each one. And so Apache Arrow is the answer for that. It's a standard for how tabular data is laid out in memory, not on disk, but in RAM. So it's a specification that says if you have a table with a string column and two integer columns, here are the exact bytes in this exact order that can represent it. And then any tool can follow that spec that can read any other tool's data directly with no conversion in between. And that's the entire idea behind Arrow. So what I'm going to go through in this video is first show you what the Arrow memory layout actually looks like, because columnar-in-RAM is a different thing from columnar on disk, and that's where a lot of confusion will live. Then I'll show you zero copy, what that means, and then where Arrow already sits in your stack, including the config flag, and then also show you Arrow versus Parquet, which is the comparison that everybody half knows. And I'll close on exactly what it is to change to get this enabled in your own pipelines as well. So most people already know that Parquet is columnar, right? Where you store a table on disk, instead of writing row 1, 2, 3, write all of column A, then all of column B. That's why Parquet files are small and why scanning one column out of 200 is cheap. And Apache Arrow is columnar-in-RAM. So it's the same idea, different place, but the consequences are very different. So picture a tiny table where you've got 3 columns, user ID, age, and country, and 4 rows for each of those. Row-oriented in memory looks like this, right? Where you have user ID, age, country, user ID, age, country, and on it goes, right? So it's kind of just looping back and forth on itself. Every row sits together, every record sits together, and it's great if you only want one whole record, which is what a transactional database usually wants. The arrow layout, on the other hand, puts all 4 user IDs next to each other in one continuous block, and then all 4 ages in a second block, and then all 4 countries in a third. And the reason why that will matter in memory is, and there's 2 of them, it's both around hardware rather than software. First is cache. Your CPU doesn't fetch one value from RAM, it fetches a cache line, 64 bytes at a time, whether you wanted that much or not. So if you're summing the age column and your ages are interweaved with user IDs and country strings, most of every cache line you pull in is stuff you're about to throw away. But if you pack the ages together, and then every cache line is 64 bytes of ages, which is the same useful data, but with a fraction of the overall memory traffic. And the second one is SIMD, single instruction, multiple data. Modern CPUs have registers that hold 8 or 16 integers at once and operate on all of them in one instruction, and that only works when the values are the exact same type and physically adjacent, which is exactly what Arrow guarantees. And Arrow even pads its buffers to 64-byte boundaries so they line up with the widest vector registries. So when a tool describes itself as having a vectorized execution engine, this is the precondition that it's talking about. The layout comes first and the speed follows from that. And then one other piece of the layout that explains a lot of Arrow's downstream behavior is an Arrow column isn't a single blob. It's a set of buffers. There's a validity bitmap, 1 bit per row, recording whether that value is null. And then you have the data itself. For fixed width types like int64, that's just the values back to back. For strings, there's an extra offset that buffer says where each string starts and stops inside one long byte blob. So if you've ever been annoyed that old pandas promoted your integer column to float the moment a null appeared, that's the fix. The nullness lives in a separate bitmap, so an int64 with missing values is still an int64. Now, the next really interesting thing about Arrow is its zero copy architecture, right? Zero copy means that two processes or two libraries read the exact same bytes in memory and not a copy of them. So same physical bytes, one buffer, which you can see here, with several readers and nothing in between. So all the different data, data types feed from the same buffer. And the precondition to this is a standard layout, right, which is what Arrow provides. Zero copy isn't a clever trick someone invented and implemented. It's what falls out automatically once two systems agree on the byte layout in advance. So if DuckDB's N64 column and Polar's N64 column are the same bytes in the same order with the same validity bitmap, then handing a table from one to the other means just handing over a pointer to that physical buffer. So there's nothing to convert and there's no time to span, and you get away from that old model of having to convert and serialize and deserialize between data types. And then Arrow specifies this information at two levels. There's the C data interface, a stable ABI that lets libraries inside a single process pass Arrow arrays around, which is how DuckDBs, Polars, and PyArrow talk to each other without going through Python objects. And then there's the IPC format, which is the same layout but written to a file or a socket, so a different process on a different machine can memory map it and read it straight. So same bytes on the wire as in memory with no parse step on the end. And if you were to do something like, hey, I want to do a two pandas operation or from Arrow operation, so you can see this kind of sample code here, right? That .arrow call and that pl.fromArrow call are effectively free, right? So you'll get a table. Number on a table with number of rows, right? And then when you make the table 10 times bigger, it's still going to be the exact same amount of time to actually query that data because you're not moving the table, you're just moving a pointer to that, right? Versus if you can, had the old naive path where you're actually having to go out to CSV and then back, it's going to take, many seconds versus under, a fraction of a second. And it'll also scale linearly if you add more and more rows versus this one will just stay the exact same no matter how many rows. And so try running this yourself with a large data set in your own machine, right? If you watching a transfer time stay flat while the row count goes up is the moment that Arrow will click for most people. And one caveat here is that I don't want you to think that every conversion is free, right? So let's say something like two pandas, a numeric column with no nulls can come across zero copy. A string column classically could not, because old pandas stored strings as Python objects, which is a completely different structure. So PyArrow had to materialize every string on the way out. And that's why some people try Arrow, call two pandas at the end and see no improvement and write the whole thing off. But you're actually rebuilding the copy at the last step. Instead, you want to pass D-type backend PyArrow, and then pandas will keep the arrows buffers underneath instead of unpacking and repacking them. So you retain that performance benefit. So now where are you actually likely to run into Arrow within your stack, right? DuckDB runs a vectorized execution engine internally and speaks Arrow at its boundaries. You can hand DuckDB a PyArrow table and query it with SQL without loading it into DuckDB first. It'll actually read your memory where it sits. Polars is built in a columnar layout that's memory compatible with Arrow, which is why PL from Arrow is instant for most types. And Pandas 2.0 shipped a set of PyArrow back D types. Strings stop being Python objects. Integers can hold nulls without turning into floats. It's opt-in, and plenty of people still haven't turned it on yet, so see if you can. And then PySpark also uses Arrow at the Python boundary, so two pandas create data frame from a pandas object, and then pandas will UDFs all go through it when you let them. And then also ADBC, Arrow database connectivity is a pretty cool new way of connecting to databases. ODBC and JDBC hand you results one row at a time. So your analytical database will produce columnar data, the driver shreds it to rows, and your data frame library reassembles it into columns at their end. Versus ADBC drivers return Arrow batches, so that whole round trip just disappears. Then Arrow Flight is the same principle over a network, right? You have a gRPC protocol that moves Arrow record batches between machines with no serialization step at the end. So a lot of really cool places where you're likely already using it or can use it without really realizing it. Now the end comparison a lot of you were probably waiting for, Parquet versus Apache Arrow. Parquet is a file format that's optimized for storing data on disk, versus Arrow is a memory format optimized for computing on data in RAM. So they share the columnar model, and they were deliberately designed to interoperate, so you're not choosing between them. The clearest way to hold the difference is to ask what each one is fighting. Parquet is fighting bytes. Storage costs money, network transfer costs money and time, so Parquet works hard to make the file small. It has dictionary encoding to replace repeated strings with integer codes. Run length encoding collapses repeated values. The whole thing gets compressed with snappy or zstd on top, and then there's a whole footer full of row group statistics so a reader can skip entire chunks without decompressing them. And all of that is excellent for a file sitting in S3 and useless for computation because you can't do arithmetic on a compressed byte range. To touch one value, you decode the page, undo the encoding, and then materialize the actual numbers. Arrow, on the other hand, is fighting CPU cycles. So Arrow is uncompressed by default, fixed width where it can be, padded and aligned to whatever the processor prefers, but you pay for that in size. An Arrow table in memory is usually several times larger than the same data as a Parquet file, and that's the trade being made deliberately because you're spending bytes to buy random access, because an Arrow int64 buffer is just values back-to-back, element 4 million sits at a known offset. It's a base pointer plus 4 million times 8, and there's one instruction and no decoding. So what actually happens when you read a Parquet file into Arrow, you're decompressing the pages, you decode the encodings, you write out Arrow buffers, and that's real work, but it's work that you're always going to do the second you wanted to compute on that data, and any Parquet reader worth using writes directly into Arrow buffers rather than into intermediate objects if it then has to convert a second time. So Parquet, think about it as the data at rest, and Arrow is the data at work. You store one, you compute on the other, and the boundary between them costs you just a single decode instead of a stack of translations. And also another thing that some people have noted, Feather isn't a separate competing format anymore. Feather v2 is the Arrow IPC format written to disk. So when you write Feather, you're dumping Arrow's memory layout straight into a file, and that's why reading it back is nearly free, and why the file is bigger than the Parquet equivalent, because it's good for a fast handoff between steps in a pipeline, but it'll be bad as your actual archive format. So that's everything I really wanted to cover in this video, just kind of a basic explainer on what Arrow is, where does it sit in the modern ecosystem, and how can you actually use it, right? Apache Arrow is rapidly becoming the standard for how tabular data is laid out in memory. Arrow is columnar-in-RAM, and that layout is what makes those single instruction, multiple data instructions and vectorized execution even possible in the first place. So the serialization tax, though, right, is the CPU and memory you spend translating data between tools without producing anything, and Arrow just completely removes that at any boundary when both sides speak Arrow. And zero copy also means that two systems read the same bytes in memory with no serialization step, and it works because both sides agreed to the layout in advance. And Parquet is optimized for storing data on disk with compression and encoding, versus Arrow is optimized for computing on data in memory with fast random access. They're designed to meet, not to compete. And Arrow is already inside DuckDB, Polars, Pandas 2.0, PySpark, ADBC drivers, and Arrow Flight. And in several of those, it's already sits behind a config flag that you'll default to off. So go and enable that today. Start using Arrow. Stop holding yourself back. I hope you learned from this video. I hope you have a great rest of your day. Data Guy out.